Let's start talking about 4.1 climate change. We've just recently covered the 4.3 topic about the carbon cycle, so you would be able to see a lot of connections here. So let's get into it. All right, some questions just to keep in mind as we're going through this lecture is, how do scientists counteract claims that human activities are not producing climate change? How is the balance of the carbon cycle disturbed by climate change? And how can we conserve species within this situation of climate change? So just some bigger questions to think about as you're learning about this topic. So this is a great picture of the Muir Glacier in Alaska from 1941 in August. And then the picture right beside it on the right is from August 31st, so same month, but in 2004. Notice how big this glacier is and how far it extends. And now we're looking at this. So the glacier doesn't go as far. It's the same exact picture, and it's mostly melted here. So just take that and reflect on that a little bit. So what is happening in these Arctic regions like Alaska that I just shown you because of this temperature rise? So what we're seeing that's unique, that we never thought we'd really see in our lifetime, is the melting of permafrost. The name permafrost is because it was meant to be permanently frozen. So this is ice on top of soil on the land portions of the Arctic. And we're noticing that that permafrost is no longer frozen in some places. It's starting to actually melt and soil is being exposed. There's also a rise in sea levels because of this ice that's normally on land that frozen is melting and going into the waterways, and that's rising sea levels. We're also seeing a change in climate patterns. So in this picture here, this is showing you, based on average temperature and the annual precipitation amount, because of those are the two factors we usually talk about when we're talking about climate. You can see the different climate zones. So when we're talking about the Arctic, we're talking about a tundra over here. So we're looking here at negative maybe 6-7 degrees Celsius on average, and it's pretty dry. It doesn't get a lot of rainfall overall in amount of precipitation. But we're seeing a change in these climatic patterns because now we're seeing them warm, and we're actually seeing soil starting to form. So if it's warmer and there's soil, you're going to have different growth, or different species start to be able to survive in this area, and other species that aren't going to be able to. So there's an expansion of a more temperate species being able to move into these Arctic tundra zones. So species you would normally find here can now move into those zones as it warms. There's a reduced range of Arctic species, so loss of ice habitat. So any of the species that depend on this ice habitat, like you've often heard about polar bears and how they use it for hunting. Baby seals, they can take the ice out and further extend into the water and hunt seals as they come up. Won't be able to as much if there's less ice. And obviously it won't fit their body structure, their amount of hair, or how they're camouflage. Those things won't work for them anymore. There's a disturbance to food chains, webs, and trophic levels. So there'll be changes in the distribution of prey species affecting higher trophic levels. So we're seeing that different prey might come into and interact with a higher trophic level than they normally would. So, and the amount of prey can change in the area, and it'll decrease in another area, especially if they're migrating. And then there's an increase in detritus decomposition. So if there's warmer temperatures, then things that normally wouldn't be decomposing and turning back into soil are going to be decomposing and turning back into soil because they're not frozen or covered in ice. So these are some of the, in general, changes that are going to happen to this climate, this Arctic climate that we normally could depend on being this cold and having this amount of rain, and then the rest would be sustainable and a pattern that was predictable for those species that live there. Also, with these areas that are normally covered in ice, it's kind of revealing different Arctic treasures, is what they're saying, as this ice melts. So different countries are kind of trying to lay claim on some of these areas so they can explore it a little more and figure out what resources they might have. Maybe it's oil, maybe it's a different type of rock material they could mine for. But areas that were not considered necessary to lay claim on are starting to be looked at and argued over. So one of the main things you need to know about we've talked a lot about warming and melting of sea ice, but there's another issue happening as the global warming is occurring. And we call this ocean acidification. So, and also bleaching of the reefs, coral reefs. So ocean acidification leads to death of coral polyps and algae. So if you remember from the beginning of the ecology unit, we talked about how the coral really depend on the zoanthial algae in order to make them survive. And if those zoanthial algae die, then the coral will also die, because the zoanthials are what's producing oxygen for the coral, and as they're doing photosynthesis inside the coral, and that gives them oxygen to survive. And also they have a relationship with food as well, and helping them have those resources. CO2, and then the reason why these corals are being bleached is because of ocean acidification. Now, why is that happening? So carbon dioxide actually reacts with water to form carbonic acid, which is going to dissociate into hydrogen and hydrogen carbonate ions. So in this picture here, you can see the atmosphere sink is up here, and then this would be the ocean sink. And the carbon dioxide is fluxing into the ocean. Now, when the carbon dioxide interacts with the water, it'll also it'll interact with carbonate ions that are in the water. When this happens, hydrogen ions are produced, and those hydrogen ions are more readily attracted to these carbonate ions, and it creates bicarbonate ions. But it also creates a lot of just singular H+ ions. And anytime there's a lot of singular hydrogen ions, it's going to change the pH to be more acidic. So ocean water is normally more basic, like an 8.2, and so it's slowly decreasing it towards the acidic end of the pH scale, which, remember, is from 0 to 14, and 7 is neutral. Fresh water is usually 7, it's neutral, and salt water is usually a little more basic. So these hydrogen ions are these extra hydrogen ions that are now being formed because of the extra CO2 being absorbed by the oceans are creating a more acidic water condition. So these reef-building corals need also these carbonate ions in order to build their skeletons, and that's not possible because they're bonding with the hydrogen plus ions and creating bicarbonate instead of bonding with calcium, which calcium, just like kind of like our nails, is what shells are made out of, and corals are made out of. And these carbonate ions aren't able to bond with the calcium, and it is forming very thin shells. So their structures are being altered because of this ocean acidification. That's happening. As well as corals are starting to die and bleaching is occurring, which you're seeing up here, as compared to when they're beautiful and colorful here. So this is going through the equation again, so it's not just the creation of carbonic acid that affects the pH, like I said. When the bicarbonate and carbonate ions are formed, these H+ ions are released, thus decreasing the pH seawater from 8.2 to 8.1. And you might be like, that's not really that big of a difference, miss, 8.2 to 8.1. But remember, the pH scale is logarithmic, just kind of like the earthquake scale when we have different magnitudes of earthquake on the Richter scale. So going from a 7 to an 8 is 10 times greater the amount. And so going from 7 to 9 would be 100 times greater the amount. So just moving these slight decimals, it may seem small, but that's a big difference in that environment, and those species aren't adapted to that. So this excess carbon dioxide that's in the atmosphere from us burning fossil fuels and adding, like we talked about in our carbon cycle diagrams, this extra CO2 that we're doing through combustion is now creating more CO2 in the atmosphere that can be absorbed into these oceans and it's having a different reaction than it normally would. So this is going through the shell, so you can see what a shell would look like at 0 days as it's forming. But when it sits in this same pH level, you can see what it looks like after 45 days. And it barely looks like a shell at all. It's thin and it's fragile. So what's at risk from ocean acidification? So marine calcifying species, so species that need that calcium to form, like oysters, clams, sea urchins, shallow water corals, deep sea corals, and calcareous plankton. The problem is they need to absorb the carbonate ions from the seawater to make their calcium carbonate in their skeleton. So that Ca, or that calcium, is going to bond with a carbonate ion. But instead, those carbonate ions are more attracted to the hydrogen plus ions in the water, and they're forming bicarbonate instead of calcium carbonate, and their shells can't form, and same with the coral. Now, who benefits from this? Technically, with CO2 being going into the water, photosynthetic algae and seagrasses would benefit because they need CO2 in order to do photosynthesis. If there's low CO2, it's a limiting factor. So they are kind of benefiting by there being more CO2 in the water. But species that are needing to form a calcium type structure, a calcifying system, they are the ones who are struggling. And remember, and kind of going back to 4.1 topic with food chains and keystone species, shelled organisms are keystone species oftentimes in a lot of food webs. So without them, that can put a whole food web at risk. This picture gives a lot of good information, and so you're going to see a picture comparing temperature with carbon dioxide. But I think what's great about this one is you're seeing the timeline here, the amount of carbon dioxide and the pH of the water, and the amount of carbon dioxide in the water. So here's the atmospheric carbon dioxide. That's been increasing a lot since around 1960, when we started really using fossil fuels more regularly and combusting them. You see the seawater CO2 start to increase, so that this is both the blue and the red are using this y-axis. And then you're seeing the seawater pH start to decrease. That means it's becoming more acidic. And I know these numbers look small because they're decimal points, but remember it's logarithmic, the pH scale. So those, even just moving a slight decimal point is a lot. So here's some facts for you. The ocean absorbs about 25% of the CO2 emitted into the atmosphere. So the ocean does a good job of helping store some of that extra CO2 that's been emitted. Therefore, the atmospheric CO2 increases, so do the levels in the ocean. Now, scientists thought this might be a good thing because then there wouldn't be as much in the atmosphere, which could help reduce the greenhouse effect that's occurring. But since the extra greenhouse effect that's occurring, But since the 1800s, the pH of seawater has fallen by 0.1 pH units. Since the pH scale is logarithmic, like I told you before, this represents approximately a 30% increase in acidity since the 1800s. So what scientists had thought would help actually didn't, and the reaction kind of has a positive feedback, meaning like it created another problem. The problem keeps increasing on the number line and getting worse. Nothing's balancing it out and bringing it back to zero. So we call that a positive feedback. So estimates of future CO2 levels indicate that by 2100, seawater could be nearly 150% more acidic. So that would be about a further decrease, 0.5 pH, to a level not seen for more than 20 million years. So this is something that we believe is just unheard of, especially for the species that are alive today. So just so you know where this data is coming from, the CO2, atmospheric CO2 is coming from the Mauna Loa, which has an atmospheric CO2 station. It's one of the first CO2 atmospheric stations that started around the 60s. And you'll see that the ocean ones are from the station in Aloha, which is taking it from the water. And then as more CO2 accumulates in the ocean, the pH of the ocean is decreasing, so they're doing pH samples of the water, and they were able to create this graph showing the impact over time. And I think that's a great visual of what you're seeing happening, and is great data to support that Global warming is not just the issue that things are getting, ice is melting, there's also ocean acidification happening. So I keep talking about the greenhouse effect. So let's get into the specifics of it. And I know that we've talked about it a little bit before, but we need to be more detailed. So the greenhouse effect is a natural phenomenon. It's a good thing. It's why the Earth is warm. So we want the greenhouse effect to happen. The problem is it's happening a little too well. So remember, a greenhouse is like a glass house that you can grow plants in, like in the wintertime, and they'll stay warm inside that greenhouse. So if you live in a snowy climate, you could grow plants in there. And why it works is because heat comes in, but then the heat can't get out. So it's basically trapping that heat and making a warmer, temperate climate in places that would normally be cold. So our atmosphere is doing the same exact thing as a greenhouse would do for plants for us on Earth. So what it's doing is incoming shortwave UV radiation from the sun comes through our atmospheric gases. So you can see it here in this picture. So shortwave, high energy radiation is emitted from the sun. 25% of that short wavelength UV radiation that passes through the atmosphere is absorbed before it reaches the Earth's surface. So it's absorbed in the atmosphere and it's absorbed by other things as it's about to get to the Earth's surface. 75% of that shortwave radiation, though, is going to reach the Earth's surface and be converted to heat. Okay? So it's going to start bouncing off things and it starts to slow down. So waves, remember, can go very quickly. That's a short wavelength because it's going really fast, like my cursor is. But a long wavelength is a slow, gentle roll. And because it's bounced off of so many things, it's starting to slow down. And it hits our atmosphere, and it can't make its way out anymore. And so it bounces back down. And the waves are getting to be so big in the wavelength of the actual wave, it's now becoming what we would call infrared radiation. Okay? So notice we have UV radiation over here, and here's the visible light spectrum that we've talked about a lot with photosynthesis. And then this all has to do with how big the waves are, though, on the wavelength that what we're talking about. So when they're short, they're like this, and they're around here in the UV light, or 400s. And when they get longer, like my cursor is moving right now, and they're more spread apart, we would start bouncing them into calling them infrared radiation. They have low energy, and because they have that low energy, they can't get out of the atmosphere, and they bounce back down, and this makes the Earth warm. So notice that once it bounces back down here, we've switched from calling it UV radiation, and now we're calling it infrared radiation because of the size of the wavelengths. So these greenhouse gases here, not the ozone layer, but the greenhouse gases here in our cloud layer, the troposphere, are what is absorbing that radiation and keeping the Earth warm. And so we need that. That's a good thing. Natural greenhouse gases are vital to the survival of life on Earth, as I said before. So, they are a good thing. Carbon dioxide and water vapor are the most significant greenhouse gases. They are the ones they absorb most of the UV radiation. Carbon dioxide sources are from cellular respiration, fossil fuel combustion, and rainforest clearing and combustion. So when we do deforestation and burn trees, that's where most of the CO2 comes from in our atmosphere. Water vapor sources are just from evaporation from oceans or lakes or rivers, and transpiration, which is evaporation from plants. So these are where these two things are coming from. And remember, they're the most significant of the greenhouse gases. There's other gases like methane and nitric oxide that have less of an impact in our environments. There might be more of them, but they don't last as long in the atmosphere, so they don't cause as much damage as these two can. Methane emission sources are from agricultural rice paddy. Methogen bacteria do methagenesis and they release methane into the atmosphere. Also, there's methogens that live inside livestock stomachs, like bacteria. So when they digest, when they release gases, they release methane, like cattle do this. Extraction of fossil fuels, as well as melting ice in polar regions, can also release bubbles of methane that were trapped inside of them as they melt. And then nitrogen oxides are usually from fossil fuel combustions like car tailpipes, as well as factories. So these greenhouse gases work very well for us. The problem is, though, that when we release too much, now the layer in our atmosphere is getting thicker and it's trapping the heat in longer. It's not able to get out into outer space. So the greenhouse effect's happening too well, and that's what we call global warming. So two factors that would determine how much influence a gas will have on the greenhouse effect is the ability of the gas to absorb long-wave radiation. Now, CO2 is really good at that, as well as water vapor. So that's why they're the most significant ones, where methane and nitric oxide are not as good as that. Also, the concentration of that gas in the atmosphere. So there's a lot of it, it's going to be a bigger factor in the greenhouse effect. So methane causes much more warming per molecule. So if you notice here, it says here that methane actually has more potential to cause global warming, but it only lasts in our atmosphere about 12 years because it actually will interact with carbon dioxide it'll interact with water in our atmosphere and make carbon dioxide. So because it changes form, it's not as much of a concern. Where carbon dioxide, notice, it only is, the warming potential is 1, but it can last in our atmosphere for 50 to 200 years, and there's a lot more of it. Okay, so there's a high concentration, and it can stay for a long time in our atmosphere. So something to also remember, though, is that the greenhouse effect has been happening for a long time throughout history, and it has gone up and down through natural changes. So global average temperatures are not directly proportional to greenhouse gases. There's other factors. For example, sunspot activity. Sometimes sunspot activity can send out massive amounts of UV radiation, which could warm our planet, like an unplanned annual event. And this can have an impact on our global average temperatures. Also, sometimes the orbit that we do around the sun, the shape of it can change. It can be more oval, it can be more circular. So sometimes we're closer to the sun, sometimes we're further away, just slightly. Sometimes our axis can shift a little bit, our tilt, and that can also impact global average temperatures. So it's not exactly proportional to greenhouse gases, but greenhouse gases definitely are increasing the global temperature to some extent. So increase in greenhouse gas concentrations will likely cause higher global average temperatures, more frequent and intense heat waves. Some areas will become more prone to droughts, so less rain, and then some areas will become more prone to intense periods of rainfall and flooding. So for example, they might have larger tropical storms, and they might be more frequent, more powerful, because with more heat, that means more water is going to be evaporated from the ocean, and that can make hurricanes become stronger or tropical storms become stronger than they were before. So the heat is what's causing it, but like for example, also in the United States, we do a lot of agriculture in the middle of the United States, but if global warming is happening, that area can become more prone to droughts. But Canada, which a lot of it is covered in cold permafrost in the more northern parts, could melt, and then they could do more farming. So some countries might be like, we're getting more precipitation, more rain, our climate has changed, and it doesn't seem that bad, but it is very different than it used to be. So changes to ocean currents can also happen. This can weaken the Gulf Stream, which would mean colder temperatures in Northwest Europe. So remember, we talked about how water takes a lot to change temperature before when we talked in biochemistry. And if you live near a body of water, that helps keep your climate a little bit more stable because it takes a lot to change the temperature up or down if you live near a body of water. And if the ocean current temperatures change, because near the surface sometimes it'll be warmer as it moves along the coastline, if it changes, for example, more fresh water going into the ocean will change the density of the water, and it could become less dense, and that area could become warmer, where other parts of the current will become colder and sink, and now it's going to change the climate along those coastlines if those ocean currents change. So overall, it's a warming that then changes climate. So we would say that the greenhouse effect, when we add more greenhouse gases, it's happening too well, and that's causing global warming, which is causing climates to change. This is called the Keeling curve. This is a famous image from once we started taking concentrations of atmospheric gas from the Mauna Loa atmospheric gas station. And so it's in Hawaii. And you can see the blue line represents the carbon dioxide increasing, and the red line represents the temperature over time. The up and down is the general seasons, though. So remember, when there is the blue is the best fit line, but the red is the seasonal annual amount of carbon dioxide. So it'll be high in the winter when there's not as many plants doing photosynthesis using that CO2. In the summer or spring, when the plants are active, it's going to be low because the CO2 is being used by plants to do photosynthesis. So you're going to see this up and down no matter what every year through the seasons, depending on what plants are active. But the blue is generally showing this increased line. So there is a strong positive correlation when we compare this to temperature between the CO2 level and the temperature's increase. So remember, this is only from 1960 to current. This one's showing a little bit further back to kind of give you an idea of from the time of the Industrial Revolution. And you can see it's not perfect, but overall, we are seeing a general increase of temperature over time. Something to take into consideration when we're talking about amount of CO2 that we're releasing is the world population size. So oftentimes it is said that industrialized countries, even though there's less people in those countries, are causing more of the global warming because we are the ones using more of these resources and releasing more of these chemicals because we have things, we have the ability to have factories and to make products, or we're the consumers buying those products no matter where they're being made at. So we're causing it more than developing countries because they have less means to do so. Like most of the time, the way that a developing country is from deforestation to clear to farm. That's usually the number one way that they're burning things in order to cook, or they're burning things to clear land to grow food for their families. And then in general, this smaller amount of people in industrialized countries is what is actually causing it. And our population is growing, so keep that in mind. After taking all of a human history for a population to reach 1 billion, like almost all of the human population or species, it took almost all of our history to hit 1 billion. It took only a little over a century to reach 2 billion in 1930. The third billion was added in just 30 years, and the fourth only in 15 years. So we are growing exponentially as a species, and we are not slowing down. So with all these people and all these resources being needed to support these people, we have to start thinking about how can we be sustainable? How can we make our environment sustainable? Here's looking at, since the Industrial Revolution, you can see different chemicals in our atmosphere. So carbon dioxide, and when you can see it starts going up, the Industrial Revolution. Methane, Industrial Revolution. Nitric oxide, Industrial Revolution. So a lot of this is because of our dependence on fossil fuels and oil, coal, and natural gas. So the sources are coming from transport, like cars, trains, and airplanes. Deforestation, burning wood, it's made of carbon, right? It's going to release carbon as well into the atmosphere. Heating homes, because we burn a lot of fossil fuels to make electricity, like coal. And then maintaining high meat diets. Cattle release a lot of methane as they're digesting their foods. And so they're also, and we don't need to have that much meat in our diet. So it's about choice, I guess, in the long run. Okay, so here in this graph, the key points that you need to see is there is a strong positive correlation between human emissions and atmospheric levels of CO2. I'm sorry. And here this big line is showing you the total anthropogenic carbon dioxide emissions. Anthropogenic means human caused. Okay, this is the Industrial Revolution where it has started. And this is where there's large increases in usage of fossil fuels. And you can see the amount goes up for CO2 levels. The dotted lines here are showing you ice core samples. So in order to get data from long ago, because we didn't really have those atmospheric sensors till about here in the 1960s, which is this black line here. The dotted line's trying to show you a best fit line, mixing the ice core data with the atmospheric sensor data. And the ice cores they drill deep into glaciers and they pull out these large cores of ice and they measure inside the bubbles that were frozen in, just like ice cubes, you see bubbles frozen in them. They measure the amount of carbon dioxide in those bubbles. And ice cores have layers, just like soil has layers if you dig deep enough. And they can figure out the time period that carbon dioxide's from, and they can figure out how much carbon dioxide was in the atmosphere at that time. So this is combining ice core data as well as the newer modern technology for the atmospheric sensors and creating a line to show how much CO2 amounts have changed over time. And we can see here that there was a large increase of fossil fuels in the 1950s. And this is where the Industrial Revolution started, where we really started making products, having factories, and using fossil fuels. So what they believe is that, and here you can see this is showing Fahrenheit. So 13.5 Fahrenheit is about 8 degrees Celsius. So it's showing you a general increase over time from 2011 to 2030 is what this picture is showing you. This is from prediction for 2046 to 2065. And this is 2080 to 2099. And what they predict, if we don't change the amount of CO2s we're releasing, the gradual temperature increase in these locations. Notice the Arctic is the most affected overall, increasing up to 8 degrees Celsius. Now, there is definitely a climate debate. There's some people who are telling people that they're deniers, that they're denying this is happening. So you can see this person's in a flooded area and they're like, it's happening, you are denying it's happening. And there's this person who's like, you're an alarmist, you're just trying to get people nervous and freaked out and fear, and he's in the city, right? So there's definitely this climate debate. So how do scientists help get people to just look at facts, right? To look at the data and analyze it, and then you decide for yourself, right? So this is a very famous graph that has been shown a lot. And so you're looking back all the way to 400,000 years ago. And remember, they can get most of this data from ice core samples. So don't be like, where did they get that data from? That's where they get it from. And then we have more current technology like the atmospheric sensors here. This is showing 1950, right about here. So yes, we were already going up, and you can see that there is definitely a general pattern of the Earth going through warming and cooling periods over time. This is 2014 here. So you can see we were well over this line where you can, there's never been a time that had been gone past that line. So this graph is very famous for showing sorry, that there's been a large increase in carbon dioxide levels, more so than ever before. And if we were to put a temperature, global average temperature line up against this graph, they almost look exactly the same. So you would think there is a strong correlation between the two. So until the past 2 centuries, the concentrations of CO2 and CH4, methane, have never exceeded about 280 ppm and 790 ppb, parts per billion, respectively. In this graph, the green here is showing nitric oxide, the red is carbon dioxide, and the blue is methane. So you're seeing this is the present, and this is going back in time before 2005, which would be the 0 mark. Current concentrations of carbon dioxide are about 390 parts per million, and CH4 levels exceed 1,770 parts per billion. This is higher than any time during the last 650,000 years. CO2 never increased more than 30 ppm during any previous 1,000-year period in this record, but has already risen by 30 ppm in the past 2 decades. So we are seeing that in this timeline, what else could be changing besides us and our technology? So are humans causing climate change? That's a good question. Most scientists would agree yes, based on the data that we're seeing, and it's because of our excessive combustion of fossil fuels. All right, so we're going to stop there. I'm going to be showing you these videos in class. Please put your notes into ManageBac, and please ask me any questions that you have at the beginning of next class, and I hope that was helpful.